A lot of its definitions, there's really only one set of calculations, and that's the pH calculations. I'm not sure if we started 8 or how far we got into it. I can't even remember. Did we get into it very far?
No.
No? Okay, good.
Going to gate.
Okay. So, we're gonna just kind of start off with the highlights of these definitions. If you want any more details, go through the PowerPoints and then go through the book. The book tends to go into too much detail for what we need. There's two definitions for an acid and base I want you to know. There's a lot more than that if I get out in the literature. I think, I've lost count. 20 years ago, it was 7 definitions for an acid. I'm sure they've changed it since then even more. But the original definitions for an acid was it produces H+. Keep in mind, H+, anytime you see that in our notes, that's a proton. So H+ is a proton. So when we talk about a proton donor and a proton acceptor, think of it as H+. It really does help. Okay. And so an acid produced a proton in water, base produced hydroxide in water. The problem is the proton would never exist by itself in water. As soon as I put that in the presence of water, this lone pair snags that right up. And then so we form H3O+. What's the name of this? Hydroxide is that OH minus. Hydronium. All right. We only memorized it 5 chapters ago. All right, so H3O plus is what we find in water. And it's actually even more interesting than that. Another water will come up and it could hit any one of these hydrogens and rip it off and make it become hydronium, and this goes back to being water. And so that proton that comes off the acid may not even be the proton that's eventually reaches our product. The protons are being scrambled all over the place. They're going onto water, and a different one comes off. It's all kind of random. And so to keep things easy, we usually talk about H+. But always keep in mind that H+ and H3O+, they're interchangeable when we're in water. Because H+ doesn't really exist in water. So the problem was, we got 2 problems here. First, the base NH3 does not produce hydroxide in water. And there's a whole series of bases like that. And so once we figured out that these were actually behaving like bases, we had to change that definition. And then this whole requirement of water was silly. And so we got rid of it. So the more general term then is an acid produces or donates a proton. It gives away H+, and a base accepts it. Even that's too restrictive, but that's just where we need. That'll get us there. So the way I use those, I'm going to take, since I've got 4 things here, I can do a combination. So I'll say an acid produces blank in water and is a proton blank. And that way I can say H+ and donor, or H+ and acceptor, or OH- and donor, or OH- and acceptor. And have a combination of this set of definitions. That gives me 4 answers just for asking about an acid. So I don't have to do a 50-50 question of the definition. Then to change it completely, all I have to do is change the word acid to base, then I get a different one of those answers. So as long as you're familiar with these definitions, that's not too bad. So the conjugate base is what's left behind after an acid does its job. So here's one of our most common acids. We've used that. What is its job? What is an acid's job?
To break stuff down.
to donate a proton. That's its only, so it's gonna give a proton. That goes off, does its thing. What's left behind? So I'm taking an H away from that, but I'm not just taking an H, I'm taking away a positive. Alright, so I'm taking away an H positive. So what's left behind? Has to be a Cl negative. What's really happening is these are sharing electrons. This H is leaving and is leaving all those electrons with the chlorine. So it has an extra electron it picked up from the hydrogen. Okay? Or you can just think of it, if I've got neutral, they gotta add up to two positives. Or I'm sorry, to a positive and a negative to cancel out. Okay. Alright, so this is the acid, this would be the conjugate base. Every acid has a conjugate base, every base has a conjugate acid. That would be what happens after the base does its job. What is the base's job? Oh, the job is always, these are kind of how you identify them. The job's going to be these. To accept a proton. Base is the only job. All right, so anything that accepts the proton is serving that purpose of being a base. Okay. So we'll be using these definitions as we go, but they sound difficult. But there's always, every acid has, so if I have H2SO4, what is its conjugate base? That's an acid. So what is going to be formed after it does its job? Well, how do I figure? What's its job if it's an acid? To donate. So it's going to give away an H plus, right? So I'm going to take that H plus away from it. What's left? SO4. Now I took a positive away from a neutral thing, so this whole thing will be a -1. Okay? Now this still has that H, and it can go ahead and it can lose another one. What would be left? SO4 with what charge? It was a negative, and I took away another positive. It'll be -2. You've memorized this one. This is sulfate, if I can make it acid. Sulfate. Sulfite is SO3. This one's actually on that list. You just didn't memorize it. This one is sulfuric acid. Get to memorize it. Easiest way of memorizing it is you start with the sulfate and you're adding H pluses until you get it to neutral. All acids end in this ic. Their names end in ic and then the word acid. Okay. So this one gave away 2 protons. So the way we describe this, how do I say 2? There's 2 di. So di and then protic, meaning it gives away 2 protons. So sulfuric acid is diprotic. There's another fancy word we learned in this chapter, amphiprotic. And water is an example of that. Water can be acid or base. It can do both. Water can be an acid or a base. And we'll play with that more. You've seen that amphi before. Where did you see that? Amphibian. All right. So we covered that last time, right? Yeah. All right. Excellent. Did we talk about strong acids? I don't think we got into those. All right. So strong acids, example being our sulfuric acid, our HCl, nitric acid, these dissociate completely. We throw them in water, they all give away all their H pluses. Goes away, all that's left around is our conjugate bases, and then these H3O pluses running around. Okay? Sulfuric acid, both the protons are strong acids, so they both completely go away. A strong base would completely dissociate. As soon as I throw it in water, sodium hydroxide splits into the OH minus floating around and the sodium floating around. Completely dissociate. Whereas weak acids, they set up an equilibrium. They don't completely dissociate, part of it will dissociate. So how do I do the symbol for an equilibrium? What's our symbol for that?
The charge times the mole.
So if it was going all the way, we'd have, this is carbonic acid. Carbonic acid is diprotic. It would go that kind of arrow. What kind of arrow do we use for an equilibrium? Just that arrow?
No.
It's going both ways, right? Good. So it goes that way and that way. So we use these two half arrows. And that means if I throw this in water, my carbonic acid will form a little bit all the way to carbonate. Doesn't go all the way in either case, either way. And so that's important because that helps me set up for our Le Chatelier's principle. Remember we said we could taste the absence of carbonic acid? And as we get rid of the carbonic acid, because it was also in equilibrium with CO2 and water, when we did Henry's law, remember? Henry's law said you increase the pressure of a gas, you increase its solubility. And we talked about CO2 coming out of your soda pop when you open the top, all right? The CO2 was reacted in equilibrium to form carbonic acid. And so as you lose the CO2, you're also losing all these H pluses because it tries to replace that carbonic acid. Goes back to here, and then that goes on to the CO2. So it's a big cycle, and you're missing out on all kinds of stuff that just disappear as the CO2 bubbles out. Okay. All right. So I want you to know on this list of strong acids, HCl, that's hydrochloric. HBr is hydrobromic. What would HF be? Hydrofluoric. And HI? Hydroiodic. Iodic. All right. Then we got to look at this one. This started off as nitrate, NO3 with a negative. You add H plus to it, it becomes nitric acid. This was sulfate, SO4 with a negative 2. It becomes sulfuric acid. All right. So our polyatomic ions, the names of those will come in handy. I'm trying to name these. Just keep in mind, acids always end with the word acid, and what suffix? Ik. All right. Okay. Strong bases have to have a metal. So in other words, over there, plus a hydroxide. Be careful. If there's not a metal, it's not a base. If there's not a metal, it's not a base. So alcohols have an OH on them. They're usually shown as an OH to indicate they're alcohols. But if they don't have a metal, they're not basic. Matter of fact, when I write carbonic acid and acetic acid is also written like this. And you see that OH and you think, oh, that's got to be a base. But notice there's no metal. So the functional group that makes an organic acid is this. and it's easy to get confused with a base. So gotta have that metal. The good news is there's only two bases that we use in the lab that are strong bases, sodium hydroxide and potassium hydroxide, because those are the only two that are soluble. Okay.
So when you're measuring like pH levels, the more acidic something is that the more hydrogen atoms?
The more,
Or is it
the higher the concentration of H3O plus.
H3O plus?
Yeah. It's also of the H plus, but remember, they're gonna be on the water, because pH only works in water. We'll talk about it in just a minute. Okay, we're almost ready. I do want you knowing the weak acids, I want you knowing both of these two, acetic and carbonic. The weak bases, the list that's in the PowerPoint is not what I want you knowing. I want you knowing this NH3. All those that are on the PowerPoint are just examples of NH3 where they've replaced the H's with some other stuff. Okay, they all work the same way. What is the conjugate acid of NH3? So here's NH3. What would be its conjugate acid? This is our base. What would be its conjugate acid? So, so every base has a conjugate acid, every acid has a conjugate base. So what is its job if it's a base? So let's take a proton and put it on here. What will we make? And now I've got 4 H's. Anything else?
Plus something.
A plus sign. Yeah, this was neutral, so we gotta have a plus. What's the name of this? Ammonium. This is ammonium. It has more stuff. This is ammonia. Ammonium has a longer name because it has more stuff. So those two are related. So the conjugate acid of ammonia is ammonium. Okay. In lab, we used an acid-base indicator. All I'll ask you about is the definition for an acid-base indicator. It just changes colors, indicates whether. There's all kinds of acid-base indicators. We use a whole bunch depending on what range we're interested in. Which one did we use in lab? That was the base we used was the ammonium hydroxide. What was our indicator?
The P word.
The P word, yeah. Nobody can. I'm not even asking you to spell it. That'd be even meaner. I got 4 bottles of it in the lab. They're all spelled differently. Different instructors can't spell it. Phenolphthalein. Phenolphthalein. What did it do? It turned pink. And it turned pink when it was in the presence of a base. When it's in the presence of an acid or neutral conditions, then it didn't change colors. We've got indicators that go from red to blue, some that go from blue to red, some that will turn green. And so we take a mixture of these different indicators and soak them into paper, and we call that pH paper. And you can dip it in and you wait and it'll change colors, and you match it to a color scale and you go, here's what the pH is. All right. So indicators are quite useful, even more useful than just the fact that they turn pink like we saw. We can get them real specific by using a mixture of indicators. Now, those are acid-base indicators. You can do an indicator for all kinds of things. You can use an indicator just for checking for CO2. So if the CO2 level gets too high, it would change colors. You can use an indicator. We'll talk later about indicators for in chapter 9 for exposure to radiation. So if you work around radiation, you gotta wear a little badge and it changes colors as it's exposed to radiation. Okay. So those are very useful. I do want you to know in this part for an acid-base neutralization, so memorize that. acid plus a base gives me a salt and water. Okay, how do you remember that? Now the example I give there, HCl plus NaO, that's the classic example. Our most common acid with our most common base, and it actually forms the compound salt. All of the classic compounds that salt is in are named after that compound. Okay. So we can form all kinds of salts, but they're all defined from this definition. Notice I wrote water as HOH. If you do it that way, as long as you write water as HOH, you can see it's a double displacement. If you write H2O, it's tough to see it. Okay. But I'll ask straight up, I'll say, what are the products in an acid-base neutralization? You'll tell me a salt and water. Okay. All right, so now we're ready for pH. We're ready for pH. Water is amphiprotic. What do I say amphiprotic means?
It should be an acid or a base.
So if I make this one an acid and this one a base, what is the acid's job? To donate, to give H plus. What will be left behind if I give H plus away? Hydroxide. HO negative, right? Or OH negative, whichever way we want to think about it. All right? What is the base's job? To accept the proton. What would be formed if water accepts a proton? Hydronium. H3O plus. Where did it get that proton? From the acid. So two waters bang into each other. One of them gives its proton over to the other. And now I've got an acid and a base. Now this is an equilibrium. This reaction is called auto-ionization. In other words, the compound does it to itself. All right? Now auto-ionization doesn't happen very often. That acid and that base, as soon as they hit each other, they react and go back the other way. But because this is in an equilibrium, it sets up an equilibrium, and it just so happens, when we talk about equilibrium, we talk about the K, and the K describes how far it goes. So if it was a really big K, we say it goes really far, almost all the way. 10,000, 20,000, it'll go all the way. If it was, the K was of the equilibrium, the KQ was equal amounts, it would be 1. So it's the molarity of the products over the molarity of the reactants. But here, if I multiply those two, I get a nice special number, and it's always 10 to the minus 14th. Is that a big number or a small number? Small number. All right? So this is always equal to that. If I make this one go up, what happens to the other one? Well, let's play with this a little bit. If I make the H3O plus go up in my equilibrium, this is an application of Le Chatelier's principle. What did he say would happen if I make this side go up? It would shift that way, right? It would shift away from the thing going up. So if this goes up, I shift that way to get rid of that extra acid. That means we use up the base. Does that make sense? If I add more acid, I'll have less base? Yeah. Yeah, you use more acid. So if I add more acid, it reacts with this base faster, and we'll have less base. We'll have more